In this video, we are recapping the content that we learned from week 2 of Statics 202, which discusses 3D force systems, as well as 3D particle equilibrium, and how we can use our understanding of particle equilibrium and static rigid bodies to find and solve for different forces of problems, and even solve for values such as measurements. So the first thing that we are going to talk about, we're going to talk about some of the geometry that we are going to be dealing with these 3D force systems. So consider we have a 3D force system that looks a little something like this. So this is our z-axis. Say this is x. So this one's x and this one's y. So if we had a vector A, which looks something like this, we would define this using 3 different quantities. So we would use our AX value plus our AY value plus our AZ value. And each corresponds to a unit direction, which is represented by I hat for X, J hat for Y, and K hat for Z, where these each represent the positive directions. So in this case, this A is in positive I, positive J, and positive K direction because it's going up, to the right, and out. If it were pointing the opposite way, then it would have negative direction. So let's talk about some quantities related to it. I'm going to talk about some angles. So the angle that it makes with our x-axis, we are going to call that alpha. The angle that it makes with our y-axis, we call beta. And the angle that it makes with our z-axis, we call gamma. So cos alpha is equal to our ax over the magnitude of A. So if we were to imagine what this looks like, so cos of any angle we know is our adjacent over hypotenuse, where this is our magnitude hypotenuse along this vector here, and this measurement here is ax. Similarly for B, cos beta equals our ay over magnitude A, and cos gamma is equal to our az over our magnitude of A. So another important definition we should make note of, let me just redraw this, is called a unit vector. So unit vectors have a magnitude of 1, which means if you took all of the components of a unit vector, added them up under a square root and made each term squared, you would get 1. So unit vector is directed along vector. So if we wanted to find unit vector A, unit vector of A would be directed along the same line of motion. Let's use a different color so you can see it better. So be directed along in the same direction as our vector, which is A. So UA is equal to the vector of A over magnitude of A. And that's what each of these components are. So we can split this A out into its components here. And when we do that, we get AX, AY, AZ, each one over magnitude A. And this looks an awful lot like our cosine ratios. So we can also write our unit vector in terms of these values. So you could also write cos alpha in the I direction. You could write cos beta in our J direction. And our cos gamma in our K direction. So those are two different ways to express a unit vector. So if you are looking to find what a vector is, you can multiply the unit vector by the magnitude. So if we are looking for vector A, that's like saying UA times our magnitude of A. All right, so let's also talk about position vectors in this slide here. So position vectors should be reviewed from Math 211 when we explored them there. So if you had a vector that starts at P and has a terminal point at Q, so if you had a vector that looks like this, you wanted to find what P to Q is, so that's our start point to our end point, that will look like taking each of our Q values and subtract it from our P values for each component. So we take our X components, then that would be QY minus PY. For J component, that would be QZ minus PZ, or K direction. So that's how we would do that. So, yeah. So where this is our start and this is our end point, we flip it around, take our last one, subtract our first one. Okay, so next I'm going to talk about some dot product rules. So again, a review. We had vector A, and we had AXI plus AYJ plus AZK. We had B, BXI plus BYJ plus BZK. So dot product is used to multiply two vectors to obtain scalar product. So if we wanted to take A and do a dot product with B, we would take each of our A components So that means we take AX, AY, AZ, and multiply it with each of B's corresponding components. And in the end, this will produce a scalar value. So that is how we do dot product. So dot product can also be expressed as a different form. So that's the first way to express it. Second way we can express it is by using the magnitude of A times the magnitude of B times cos theta. So this is useful when you want to find the angle between two vectors. So find angle between vectors. So because of this principle, if A and B are parallel, our theta would equal 0, and thus cos 0 is equal to 1. So then our dot product, which is equal to the magnitude of A times B. Now, if A and B are perpendicular, then our angle is going to be 90 degrees between them, and our cos is going to be equal to cos 90 equals 0. So then A dot B would equal 0. Okay, so that covers everything we need to know for dot product. And finally, for projections, the equation that we use for F projection, so our projected force, is our force dot product of our unit vector, an arbitrary point. So this means the unit vector must end at F's origin. So what that means is if we had a system and we had F starting here, it's a Cartesian plane, our unit vector would be represented as such, because it doesn't really matter where it starts, but it must end at F's origin, where this is F. Let's do F in a different color. This one here is our force. Okay. So now we're going to move on to talk about particle equilibrium. So when we are solving three-dimensional questions, we want every single part of our system to be in equilibrium. So what does this mean? This means that all of our x components of force are equal to 0. The sum of our force y components are equal to 0, and the sum of our z forces is also equal to 0. So this is going to help us when we are exploring problems that look complex, but are relatively easy to solve. And this just ensures that our overall magnitude of force for our system is equal to 0 if each of these terms are 0. Okay, so let's talk about springs and cables and weight. I forgot to add that to here. So these are different kinds of forces. So just for a brush up, for springs, we use the equation F equals spring constant times our change in our length. So I'll write this in plain English terms. So spring constant. This will either be given to you or you will be finding it. It's just a number. And our change in our length is the stretched length minus our unstretched length of our spring. So, moving on to cables. It's not really an equation for this. For cables, we assume they cause tension. So if I were to draw, say, a pulley that had two cables pointing from it, and I wanted to draw a free body diagram, or actually no, sorry, this is the free body diagram. So if I had a pulley here that had a cable going across it like that, if I were to draw a free body diagram of that, it'd be causing tension, so you want it to point away from the body you're measuring it on. So this would be our tension force. And lastly is weight. So this can often slip through the cracks, but just make sure that weight is directed downwards and is equal to the mass of an object times gravitational acceleration. Okay, with that being said, let's try our hand at some problems. In this question, we have a tower that is being held in place by 3 cables, which are under tension. If the force of each cable acting on the tower is shown, determine the resultant force in Cartesian form acting at point D of the tower. Also determine the coordinate direction angles alpha, beta, and gamma of the resultant force. Take x to equal 20 meters and y to equal 15 meters. Okay, so answering in Cartesian form just means that we are going to be answering with our I, j, and k directions separated. So the first thing we have to do is find point coordinates. So which points are we talking about? We are talking about where it's being anchored and where it originates from. So we have point A, B, C, D, and our origin. So we are going to find the X, Y, and Z locations for each of those points. So let's start with A. So A is located, so X is 20, Y is 15. So that means we need to assign what's going to be positive and negative. Okay, so obviously this is going to be positive Z. I say this is going to be positive Y this way, and then positive X this way. So for A, that means we are going down, so that is in our negative X direction, negative 20. Then we're going in our positive Y direction, 15. And we are not moving up, we are anchored to the ground, so that means we have no Z component. For point B, same thing. So now we're in positive X and Y. So positive X direction, we have 6. Positive Y direction, we have 4. And it's also anchored on the ground, so Z is 0. For C, we are located in negative directions both ways. So we are in the negative 16X and negative 18Y. If we moved it that way, Y direction, and we're also on the ground. For D, we are at, so we are dead center in our origin. We are just at a height of 24, 0, and 0. So now what we're going to want to do is find position vectors. Okay, so we want to look at matching them up with the vectors that come from D and go to each of our points. So in this case, we want to look at D to C. We want to look at, this is D to A. And we want to look at D to B. So when we do this, let's start with our DA first. So to recap from the slides that we did above, if we're going from D to A, we are taking our A components and subtracting it from our D components. So in that case, that would be negative 20 minus 24i plus, then this is 15 minus 0j, and plus our A minus our D. Okay, sorry, I made a mistake. This is meant to be 0. Okay, and that gives our position vector as negative 20i plus 15j and minus 24k for DA. Let's do DB next. That's equal to B minus D, so that's 6 minus 0. And that's 4 minus 0. And then that's 0 minus 24. That's going to equal 6i plus 4j minus 24k. There's dB done. And lastly, we have dC. You know the drill, C minus our D, so that's negative 16 minus 0, I. That's plus negative 18 minus 0, J. And that's plus 0 minus 24, K. That's negative 16I minus 18J minus 24K. All right, so those are the three position vectors for our three forces. Our forces don't quite come into play yet, because what we need to do next, we need to find our unit vectors. So our unit vectors for each of these, so we know that unit vectors are equal to a vector over the magnitude of a vector. So if we were to do that for dA, for example, that would be equal to our dA vector in Cartesian form over the magnitude of dA. So that would look like, so we have our negative 20i plus 15j minus 24k, and that's over negative 20 squared plus 15 squared plus minus 24 squared, all under that square root. And then we separate each component. So let's see what our denominator is. plus 15 squared plus 24 squared. And that's 34.655. So let's do that divided by each of our components. That's negative 20 divided by that. It's going to give negative 0.577i, 15 divided by x, plus 0.4328. Sorry, that's j. And that's minus 0.692k. That's our first one. Repeat the same step with u db. That's 6i plus 4j minus 24k. That's over 6 squared plus 4 squared plus negative 24 squared. And that's equal to 36 plus 16 plus 24 squared. It's equal to 25. So then when we do store this is 0.239i. And then that's 4 divided by our denominator. That's plus 0.159j. And negative 24 divided by that is minus 0.958k. Last one. So that's DC. Then over, I'm not going to write it out because you guys should already get the gist of it. So that's 16 squared plus 18 squared plus 24 squared under the square root, and this is over 34. So negative 16 over 34. This is going to be negative 0.471i. Then negative 18 divided by 34 is minus 0.529j. And negative 24 divided by 34, negative 0.706k. Okay, so those are all of our unit vectors, which we used our position vectors in order to find. And lastly, we want to find each of our forces in Cartesian. That means we are going to take our unit vectors and then multiply them with our corresponding force. So if we were to do dA first, we see that it's 400 newtons. So we're going to multiply each term in here by 400. That's going to equal times 400. This is negative 230.844i. Then our next one, 0.4328 times 400. This is 173.12. And then minus 0.692 times 400, minus 276.8k. So that is what our force is in Cartesian form for dA. Do the same thing for FdB. That's equal to 800 times our unit of dB. So that's going to be 800 times 0.239. That's 191.2 I. Uh, 0.159 times 800, which is equal to plus 127.2 J, then minus 0.958 times 800, and this is minus 766.4 K. Then our FDC, last one, is equal to 600 times our unit vector of dC, which is equal to negative 0.471 times 600. This negative 282.6 I, then negative 0.529 times 600. This is minus 317.4 J, and minus 0.706 times 600, which is minus 423.6 K hat. So those are the Cartesian forms of our three forces of cable tension. So now in order to find what our resultant force is, we are going to add up all of our X, Y, and Z components. So resultant force. So our resultant force of our Fi components will be negative 230.844. It will be plus 191.2 and minus 282.6. That will be equal to that's minus 322.244. Our J components added together, that's 173.12 plus 127.2 minus 317.4, 173.12 plus 227.2 minus 317.4, and that's negative 17.08. And in our K directions, we have negative 276.8 minus 766.4 minus 423.6. It's negative 276.8 minus 766.4 minus 423.6 plus negative 1466.8. Yeah, and those are within the neighborhood of our answers. The signs are different for our X one, but that's because we just assigned it differently. But yeah, so that leaves our F resultant force in Cartesian form as negative 322.24 I minus 17.08 J minus 1466.8 in our K direction. Okay, and last step is to find our cosine angles. So we know based on our first slide, we know that our unit vector is equivalent to, our unit vector is equivalent to cos alpha, cos beta, and cos gamma. So let's find our unit vector first. So we want to find a resultant unit vector. So that's going to be So we're going to take our unit vector in Cartesian form for our resultant force. And we're going to take it over the magnitude of this. I'm not going to write it out, but you guys should know what I'm talking about. So we're going to have this one squared plus and that's going to be over 15.01. Sorry, 1501.877. I'm going to store that value. So our first value, we have negative 0.21456 in our I direction, minus (0.0113) j minus (0.9767 k). Now each one of these is equal to cos alpha, this is cos beta, and cos gamma. So then, using that, 21456, alpha equal to 102.389 degrees. Cos beta is equal to negative 0.113, which is going to give us 90 degrees. And lastly, gamma will give us negative 0.19767, and that's going to give us an angle of 167.592, and these are our angles. All right, so it's a bit of a long question. There's definitely a lot of work that's involved in solving it, but once you get down to the steps and you develop your formulas to help solve each of your separate components, then it becomes a lot easier to understand. So just make sure you're really careful in the beginning when you're finding your position vectors, because if you switch around the order that you subtract in, that could mess up your calculations. And make sure that your coordinate system is defined to ensure that your results are consistent. So that brings us to the end of the first part of week 2 review. The second video will be covering some more examples talking about 3D force systems and 3D particle equilibrium. Thanks for watching.